Hello everyone. I have a pretty good problem. A long time ago, I had made this problem. Um, so there is this problem in which you can imagine um, a ring-like structure which you can rotate. Other parts of the structure is not really shown, but you can say there is a spokes here, and there's a shaft here, and you're just trying to, and you have a finger here trying to rotate it. Okay, so you're rotating it, and there is a metal piece that's it's rubbing against here as rotating, and this metal piece has a wire that goes in and this is a voltmeter, and the wire comes, and there's another metal piece which kind of rubs outside of it. And just forget about the friction and rubbing and those things. That's not so important here for this problem. And the magnetic field, is going right through, like this. Magnetic field through this. So magnetic field is through this material. This magnetic field through that material. Magnetic field comes in here. Magnetic field goes out like that. So magnetic field is constant magnetic field. This magnetic field is constant and just rotating in the magnetic field. All right. So you will find that there is a voltage set up in this voltmeter. Will show there is a voltage between inner edge and the outer edge, and it looks pretty complicated if you just attack it using. So if you use the Faraday law, so EMF is E dot dl in a closed loop is equal to minus d dt of some surface b dot n hat dA. So you have to think of some loop, and this area, this surface is surface attached to the loop, and that's the problem here that you may run into. Okay, so the way you might think is, okay, what is the loop here? Is the loop something like attach it here, then come edge of the surface here and go through here, and then so this is the loop, and the area would be so there is a flat area here, and then there is a, you might say, flat area here, and then then you come out, and then what is that area? So so it's not very clear. It's like this area is not flat. This is so this is this area that's going through. So you have to see if this flux through this area, which in that's actually turns out to be a wrong way of thinking. And here area is, you think area will be, this part will be somewhat fixed, and this is fixed, this will give me 0. But that's not the case. Actually, the area here is being dragged, is kind of, this is the function of time, and that's what the problem is. So I will not do it this way. There's another way of doing it, is to think of that no matter at any point, so let's take any point. So let's look at any point of this thing. So let's I'm going to just put a point over here, somewhere in the middle. Okay, so this is somewhere in the middle, a point in the middle. And so this is like this is the point inside there. And if I look at a charge Q, so you have an electron, say, and these are the conduction electrons in this metal, a conduction electron. So it has a velocity v in that direction, whose magnitude is omega times distance is r, omega times r. Omega is this. So omega vector is, right hand rule. So at the vector points up, but the omega is the magnitude and velocity is in a circle. So this electron is going in a circle, let's suppose. Okay. Now, because it's going in a magnetic field, so if this particular electron will have a magnetic force pointed in that direction towards the center. Okay, so it will be pointed radially. So that's the magnetic field Fm, which means this, unless there was some other force, this electron will just start to accumulate on inside thing, and so outside will become a little bit positive, right? It will become a little bit positive, outside surface, and inside surface will become a little negative. Well, there will be if you continue it for a while, it will come to a stable situation where the force on this electron will be not just magnetic field, but there will be a force, electric field, which will be balancing these two. So electric field, so we have a electric force is E, and the distance at point P. So we just call that point P. So we have at point P. And magnetic field is going to be E, and V cross B, and they're 90 degrees to each other, so this will just be VB, and it's pointed towards the center, so away from center towards center, and so that V is going to be omega times R. So E omega RB, and in equilibrium they will be equal in magnitude, opposite in direction, they will cancel each other. So EP will turn out to be omega times B times R, and P is a point that a distance R away. So it depends on where the charge is, right? So I'm going to write E as a function of R is omega BR. So this is very important because I can now, in here, you can say, let's put this thing directly, not over here, but across here. So this will be so looking from that edge. So I will have so looking at the cross section, we have this, and our origin is here, and some point is R, and electric field is pointed this way, and so if I just integrate across this, I am going to, so what I want, that part of the EMF that we want is from this integration from R equals to R1 to R2. So R1 to R2, inside is the most negative and outside is the positive. So going from negative to positive, so the delta V will simply be E dot dl, and the dl is just dr. So dl is just dr. So this is in the same direction. So I said E dr, and so we are going to get E is this, omega b is constant. So this is just going to be omega b r dr. Omega b is constant. Omega b comes out. Very easy, right? Omega b and r1 to r2 r dr, which is just omega b over 2 r2 square minus r1 square. So let's look at some of the signs we kind of swept aside while we're doing this calculation in a dirty way. I just want to get this will be positive, the way we have kind of written down. Just this give me the voltage. So if I were going to release, so I'm integrating from R1 to R2. So this is r hat dr. So this is in this direction, and you have a E is going inward, so it's minus E er r hat or u hat r, and this is u hat r. So I should delta V is minus r1 to r2 E dot dl, as you remember. So there's a minus sign I had actually absorbed when I was doing this calculation, and this minus with this will actually be E dr with the minus sign, and so this minus sign and this minus sign will cancel, and so r1 r2 E at r dr as we have done over here. Okay, and that's the answer for this problem. So how do we do using this? You say, okay, oh, you got this, okay, great, so you got the answer, but could I have done another way? So this is my preferred way, and the other way I'm going to explain also. Okay, so there's another way of doing this. Okay, so what's the other way where I can make use of this formula? EMF is E dot dl. This is induced EMF. It's usually written like this: minus d by dt of some. So this is a loop, and this is surface that bounds the loop. The surface that's attached. This is surface that's attached to the loop. Okay, and this is B dot n hat dA. dA is an element of that thing. So the right side, usually when you apply use this method for solving this problem, you think of the right side as minus some delta t, and this stuff at t plus delta t minus the stuff including this surface, okay, at t. And it will help us to kind of do recall something that you learned some time ago. So there was a problem long time ago, is say magnetic field is say pointed towards us, right? Suppose you take a magnetic field which is pointed towards us, and we'll denote it like this. and then you take a bar of length L, and you want to move this bar at speed v. So between this point A and B, what's the delta v of A between point A and B? Okay, so there will be potential difference that will set up. And the way we did this problem earlier to get this answer, if you did that, you will find that it's electric field. If you did the electric field in here, electric field will be V times B. This will be induced electric field. And because there's no distance, we can integrate from A to B, and from integration from A to B of ED, let's call this y-axis, EY dy, and this will give me VBL. So that will be the answer. But that answer can also be obtained by looking at, say this is at time t, and then it's over here at time t plus delta t. So the situation is this at time t plus delta t and time t. So in terms of this, we can say that this is the area through which flux has, the area will be that area compared to when there was no magnetic field in that area. So it's kind of swept out that area. So when you compute phi, so it will be phi, before this area is empty, we can say empty. So phi at t plus delta t minus phi at t over delta t, we're looking for this. And so phi t plus delta t is now this much area. Originally it was, this area was just this. This loop was just, so this was 0. And this one, now the loop is this big. So basically this has changed. This changes, this is fixed, but this is changes. Okay, and so this, say V times delta t times L, so this is the area, times B minus 0 over delta t, and so we get BVL. So this way is using the Ampere's law, and this way is also using Ampere's law, but it's called we just induced EMF from so-called mechanically induced EMF. There are two methods. So we used mechanical earlier. Now we want to use this in this way, and very similarly we will do that over here. Okay, so if you look at here, let's look at one of the cross sections here. So I'm going to think of like this part. Okay, so I'm going to think of this part, and so at time t, it's over here. So this like a bar is over here, and time t, this time t, and that would have rotated over there. So let's look at it. This is, let's look from the top and draw it in XY plane. So this is this is XY plane. Okay, so let's look at and let me stop it and draw it. Okay, so now I've drawn it out. So this is in XY plane. So this is XY plane, and magnetic field is in that way. So we just drawn the XY plane, and this is a cross section like that, and so this distance is r1 and this distance is r2, and it was over here. So you can think of this as a bar rather than the entire thing just looking at cross section. So it's kind of like a bar. If you prefer, you can think of like a physical bar. So we're looking at a small thickness of this, and we want to know what's the EMF across this. So it's exactly like the bar problem, but instead of the bar was going this way, the bar is kind of rotating, with radially, right? So this bar, the loop has a let's write down the loop. Loop will be like this, coming back to 0 as t equal to 0. But t, so t equal to t, and this t equals to t plus delta t is somewhere here. Now the loop is the second arm of this loop is out here now. So we need flux through this, which will be relevant for the right side. So B is perpendicular to this. So B is perpendicular to this. That means n hat is parallel to this, and B is constant. So this just becomes flux at t plus delta t. Flux at t is 0, and flux at t plus delta t is B times the area of this, right? So it's kind of like a little rectangle, but delta t is 0, so delta t is going to 0. That's the limit we want. So B, if you look at this side is R2 minus R1, and if you look this side will be omega r theta, right? So it will be omega delta t. That's the theta part. And times the average of these two, r1 plus r2 over 2. So this is so omega r theta, that's the distance. So this will be the area, and so we get B times omega times B r2 minus r1 times r2 plus r1 over 2 times delta t. So now we want EMF, so phi t plus delta t minus phi t over delta t. This will give me omega b over 2. Now I can make a product of this r2 square minus r1 square, and I think I have got the same answer. Now this is another way of doing it, and now using actually mathematical formulation of Faraday law, but this is much more convoluted and looks a little bit difficult to apply, and that's why my preferred method is the one that we did the earlier way. Okay, so that was a good little bit sidetrack, okay, so that's it. If you haven't subscribed, please subscribe, and I appreciate if you can hit a like button if you like it. You can also go check it out, this website that I maintain, and also this is the actual publication of my book, which you can go out and check out at openstacks.org, and this problem is from that website. Okay, take care, bye.